Dear students, myself Dr. Sridhar, Assistant Professor of Mathematics, Government First Grade College, Goka. So today I am taking the rings and fields. So in the last class we have learnt the rings and its properties. So today we learn some more types of rings and we prove some theorems. Okay, so let us start. So first we have a ring with 0 divisors. A ring with 0 divisors. So a ring with 0 divisors means if for all AB belongs to R, A is not equal to 0 and B is not equal to 0 implies AB is equal to 0. AB is equal to 0. That means what? If both A and B are not equal to 0, but when you take the product of those two, then it should give 0. It should give 0. So then the elements A and B respectively are called as a left 0 divisor and right 0 divisors. That is, A is called as a left 0 divisor and B is called as a right 0 divisors. Next comes a ring without 0 divisors. So if for all AB belongs to R, A is not equal to 0 and B is not equal to 0, then AB is also not equal to 0. Okay, so if both are different from 0, and the product is also not equal to 0, that means what? AB is equal to 0. AB is equal to 0 implies either A is equal to 0 or B is equal to 0. Either A is equal to 0 or B is equal to 0. This is also correct and this is also correct. Okay, if for all AB belongs to R, A is not equal to 0 and B is not equal to 0 implies AB is also not equal to 0, or AB is equal to 0 implies either A is equal to 0 or B is equal to 0. So to get AB is equal to 0, one of the two members, that is A or B, is equal to 0. Next comes, so we shall see the examples pertaining to these concepts later. Okay, so now next we define an integral domain. So if a ring R is commutative ring, with unity and is without 0 divisors, then it is called as integral domain. Already in the last class we have seen what is a ring R with commutative ring with unity. In the last class we have defined commutative ring with unity. Okay, so a ring R is commutative ring with unity and also is without 0 divisors. Means what? It should satisfy this law. So a ring R is commutative ring with unity, along with it should satisfy this property, that is, for all AB belongs to R, A is not equal to 0 and B is not equal to 0 implies AB not equal to 0. Okay, then it is said to be an integral domain. So for examples for integral domain is a ring of integers. So ring of integers is an example of an integral domain. Similarly, rings of rational numbers and rings of real numbers are all integral domains. So for example, take a set of integers. So set of integers means what? What numbers will come? So 0, 1, 2, 3 and so on. So in that if you take 0 into 2, you will get, that is 0. 0 into 2 is, you will get 0. So one of the member is 0. So therefore the product also gives 0. So either A is equal to 0 or B is equal to 0. Then AB, it should give AB is equal to 0. For example, A is equal to 0. Take 2 into, so here 2 into 0 is equal to 0 because one of the member, that is one of the member is 0. One of the member is 0 and other member is not 0. So therefore 2 into 0 gives 0. 2 into 0 gives 0. So therefore set of integers is an integral domain. Similarly, the set of all real numbers, ring of all real numbers, a ring of all rational numbers is also an integral domain. But ring of integer modulo 6 is not an integral domain. ring of integer modulo 6 is not an integral domain. So why? Let us take an example. So ring of integer modulo 6 means what here? So here the set contains the element, say S is equal to, it contains the element 0, 1, 2, 3, 4 and 5. So this is a ring of say a ring of integer modulo 6. Modulo 6. Integer modulo 6 means always the set contains the number less than this one. So means what? 0, 1, 2, 3, 4, 5. Suppose if ring of integer, so ring of integer modulo 6 means in this case always set contains the elements 1 less than 6. Means if ring of integer modulo 6 is, then the set contains the elements up to 0, 1, 2, 3, 4, 5. Suppose if the ring of integer modulo 8 is there, then the set contains up to 7 elements. So 0, 1, 2, 3, 4, 5, 6, 7. If the ring of modulo integer 9 is there, then the set is always 0, 1, 2, 3, 4, 5, 6, 7, 8, up to 8. So like that, this is a ring of integer modulo 6. This is a ring of integer modulo 6. So now take any two elements, say 2 into 2 and 3. Then here the operation is multiplication modulo 6. Multiplication modulo 6. Now if you multiply these two, what will get? 2 into 3 is 6. So now 2 into 3 is 6. So means that 6 is more than this number, that is 5. 6 is more than this number, or the 6 does not contain in the set yes. The 6 it does not belongs to the set yes, and it is more than this 5. So what we do is we divide this 6 by 6. We divide this 6 by this 6. So 6 ones are 6 and the remainder gives 0. So 0 is the answer. So when you multiply 2 into 3 by the operation multiplication modulo 6, you will get the answer as 0. That means here 2 is not equal to 0 and 3 is also not equal to 0, but their product we are getting as 0. Their product we are getting as 0. That means it is a ring with 0 divisors. It is a ring with 0 divisors. But according to the definition of the integral domain, it is a commutative ring with unity and is without 0 divisors. So therefore the set of integer modulo 6 is not an integral domain. Is not an integral domain. Okay, so next we define the term field. So field means a commutative ring F with unity having more than one element is called a field. If every non-zero element of F has a multiplicative inverse in F. Or we can say that for each A belongs to F, A not equal to 0, then there exists an element A inverse such that A into A inverse is equal to A inverse into A is equal to 1. So if this condition is satisfied, then the commutative ring with unity is called as a field. Okay, so now we prove some important theorem, theorems. Theorem says that every field is an integral domain. Every field is an integral domain. This we have to prove. Okay, now proof. Okay, so what we have to show? Every field is an integral domain. So let F be a field. Let F be a field. Okay, let F be a field. Then according to the definition of the field, then F is a commutative ring. F is a commutative ring with unity. Okay, with unity, and is commutative ring with unity such that commutative ring with unity such that every non-zero element of F has a multiplicative inverse. Okay, this is according to by the definition. So we have taken let F be a field. So then F be a field means, according to the definition of the field, F is a commutative ring with unity such that every non-zero element of F has a multiplicative inverse. Every non-zero element of F has a multiplicative inverse. Now to show that F is an integral domain. So what we have to show? To show that F is an integral domain, we have to show that F is a commutative ring with unity, okay, and is without zero divisors. So if this we have shown, then F is a integral domain. So to show that, what we have to prove is F is a commutative ring with unity and F is also a ring without zero divisors. So this we have to show. Now already we have taken F is a field. Field means F is a commutative ring with unity. So that is proved. Means no need to prove that, because F is a field. So field means it is already a commutative ring with unity. So only the thing we have to show, F is a ring without zero divisors. F is a ring without zero divisors. Okay. So already we have to show that F is an integral domain. So it is sufficient to show that AB is equal to 0 implies either A is equal to 0 or B is equal to 0. Okay, this is by the definition of the integral domain. What we have to show? It is sufficient to show that AB is equal to 0 implies either A is equal to 0 or B is equal to 0. This is by the definition of a ring without zero divisors. Okay. So that is, we have to show that AB is equal to 0 implies either A is equal to 0 or B is equal to 0. Okay, so now let us consider AB is equal to 0. Now first assume that let A is not equal to 0. So then according to A is not equal to 0 means there exists an inverse A inverse. Okay, so therefore operating A inverse on this. Okay, so therefore A inverse of AB is equal to A inverse into 0, or A inverse into A is E into B is again B, so which is equal to B is equal to 0. So similarly we take let AB is equal to 0. Now here we assume that let B is not equal to 0. Same. So then there exists an inverse of B. An inverse of B, that is B inverse. So now operating B inverse on this AB, so which gives B inverse of AB is equal to 0, which means that B inverse of AB is equal to BA, because it is a commutative ring, or is equal to 0. So B inverse into B is A, E into A is equal to 0, which implies A is equal to 0. A is equal to 0. So therefore F is an integral domain. Therefore F is an integral domain. So this completes the proof. Okay, so in the next class we take another theorem. Okay, thank you.